Again, take out your highlighter. Characteristic 2 has to do with horizontal and oblique asymptotes. And with horizontal and oblique asymptotes, there are 3 situations that can arise. And those 3 situations are the same as the 3 groups that we saw in section 2.2. Wow. The first one, situation number 1, which we've dealt with already. Is when you have the same degree on the top and bottom of your fraction. For example, we have 3x squared plus 5x over 2x minus 7x squared. The biggest degree on the top is an x squared. The biggest degree on the bottom is a negative 7x squared. Any time that the degree is the same on the top and the bottom, you will have a horizontal asymptote. And you look at your biggest degrees, and whatever the coefficients of your biggest degrees are, that's going to be your horizontal asymptote. Situation number 2. Is when you have a bigger degree on the bottom, a bigger degree in the denominator. Our example could be something like y equals x plus 7 over x squared minus 11. A bigger degree on the bottom will always result in a horizontal asymptote, and it will always be at y equals 0. And the third thing that could happen is when you have a bigger degree on the top or in the numerator, and in a situation like this, this is where we're going to get an oblique asymptote. Now remember from example 1 that we wrote out all the steps for graphing. Horizontal asymptotes and oblique asymptotes is step 2. You always complete step 1 first. So I want you to just temporarily look back at example 1, because I want to point out something that happened in example 1. In example 1a, notice that we have a higher degree on the top than we do on the bottom. And one of the mistakes that students make in a question like 1a is they look at the question and right away say, there's an oblique asymptote, because there's a higher degree in my numerator. That's not the case, because you always have to do step 1 first. In step 1 first, you factor first and find all vertical asymptotes and or holes. So when I factored it, my x plus 5 canceled out. And when something cancels out and makes a hole, and this is why I wrote this in blue, you now have to graph the simplified equation. The simplified equation is just a line. It's no longer a rational graph that we have to deal with. There's no oblique asymptotes. You just have to graph the line and add the hole. So when we write out here with our oblique asymptotes, it's a bigger degree in the numerator. That's after the fact that if you had to simplify something with a hole and things disappeared, you may no longer have that oblique asymptote. You're always going to graph the simplified version if there's a hole. So let's look at, they've got 3 examples here. The first example. What's the largest degree? It's an x to the 1. What do we have? Do we have situation 1, same degree, bigger in the bottom, or bigger in the numerator? Well, our x is in our denominator. It's bigger on the bottom. So we would be able to look at this right away and say there's going to be a horizontal asymptote at y equals 0. The textbook goes into a much more mathematical explanation of what happens when x gets really, really big. Well, when x gets really, really big, you're dividing by a really, really big number, and that means it's going to get close to 0. Example number 2, okay? Again, we notice that it has the same degree in the numerator as it does in the denominator. You can just directly go from there and say that there's a horizontal asymptote at y equals 2. They're using synthetic division to explain it to you. Don't worry about that. You can just say horizontal asymptote at y equals 2. Let's keep it simple. And finally, how do we find an oblique asymptote? That's the one thing we haven't talked about or at all yet. This is where you will have to use synthetic division. So it's going to be a little review of chapter 1. What do? We take the equation x squared. In synthetic division, that's 1x squared, 0 x's, and 0 constants. We're dividing by x plus 1, so you put a minus 1 out in front. Bring the 1 down, multiply, add, and whatever you get, you can ignore the remainder. Doesn't matter how big that remainder is. It could be 16 billion. Doesn't matter. The equation you get after you divide y equals x minus 1, that is going to be your equation of your oblique asymptote. So if we go to example 2, we're going to do all of the steps and graph these completely. So first of all, always factor first. This factors to be x plus 7, x minus 1. Step 1. We have a non-permissible value. X can't equal negative 2. Step 1 figures out holes or vertical asymptotes. The minus 2 is going to be hole or vertical asymptote? Since that x plus 2 doesn't cancel out, we're going to have a vertical asymptote at x equals 2. So I'm going to start graphing it as we do our steps. There's our vertical asymptote at x equals 2. Yes. Yes, it should be at a negative 2. Thank you. So, there we go. You can do that on your notes. Yes? No? You can just erase it. Sorry about that. Yes, it's at x equals negative 2 because that's our non-permissible value. Secondly, we now look at step 2. Nothing simplified, so we're still graphing our rational function. When we look at our original equation, where's the biggest degree? Or are they the same? We have an x squared on the top. We have no x squareds on the bottom, so the biggest degree is in our numerator. That means in this case, we're going to have an oblique asymptote. To find the equation of that oblique asymptote, we're going to need to use synthetic division. So set up our synthetic division. X squared plus 6x minus 7 divided by x plus 2, so we'd have a minus 2 out in front. Bring the 1 down, multiply, add, multiply, add. We can ignore the remainder of minus 15. And y equals x plus 4 is our excuse me, oblique asymptote. So how do I graph that? It's a straight line. I have a y-intercept at 4. I have a slope of 1. So over 1, up 1, over 1, down 1. And draw my asymptote. Label it with its equation, y equals x plus 4. Step 2, done. Step 3, we're going to find our y-intercepts and our x-intercepts. Again, how do you find a y-intercept? Plug in 0 for x. I'll go to my original equation because that's going to be the easiest. It simplifies really quick. Can you see that you'll get negative 7 over 2? So our y-intercept is 0, negative 7 over 2, or negative 3.5. I can draw that in my graph. Negative 3.5. X-intercepts. Again, here it's really helpful if you use that idea. For an x-intercept, I plug in 0 for a y. I've got 0 equals a fraction. The only time a fraction is equal to 0 is if your numerator is equal to 0. And since my numerator is already factored, I can tell that I'm going to have one x-intercept at negative 7 and the other x-intercept at positive 1. Step 3 was also drawing any other important points. You need one per section. So again, our vertical asymptote separates our graphs into sections. We only have one vertical asymptote, so our graph has 2 sections. Have we labeled any points to the left of x equals negative 2? Yes. Have we labeled any points to the right of x equals negative 2? Yes. So we do not need to graph any more points. We can now just draw the graph towards the asymptotes. So what does that mean for this graph? Well, with this point, negative 7, I need to go towards both the asymptotes. It means it's going to go down towards this one and then up towards that one. Discontinued. And in the other section, it's going to go up towards that one and down towards this one. And this is our final graph, and this is what our graph with an oblique asymptote looks like. You don't like it? No. Yes? The x plus 4 comes from synthetic division right here. If you wrote out your division statement, you would have x plus 4 remainder 15 of negative 15. But you ignore the negative 15, and what you get with synthetic division is going to be your oblique asymptote. Let's look at our second graph. Again, factor first. Step 1, what are our non-permissible values? X can't equal negative 7 and x can't equal positive 1. Do they cancel out? No. So in this case, both of these are going to be vertical asymptotes. Oops. So x equals -7 and x equals 1 are vertical asymptotes. 2. We have now a higher degree in our denominator. Higher degree in our denominator means we're going to have a horizontal asymptote, and that horizontal asymptote is always at y equals 0 in this case. Step 3, x-intercepts and y-intercepts. Y-intercept, plug 0 in for x, go to your original equation, and you'll get 0,2 over -7. So if I was graphing that, that would be right there. X-intercepts, if I put in 0 for y, is my fraction ever going to be 0? Well, is my numerator ever 0? Yes, I can make my numerator 0 when x is -2. So this is the first time that this is happening on an actual graph for us. We have a point on an asymptote. Remember, that can happen on horizontal asymptotes. It never happens on vertical asymptotes. But since horizontal asymptotes are just telling us what happens at extremes when x gets big, positive numbers, or big negative numbers, you can, as is this case, have a graph go through an asymptote in the middle. Okay. Now, do we need any more points? We have 2 vertical asymptotes, which separates our graph into 3 sections. You have none in this section to the far left. You have none in this section to the far right. And even in the middle, you're going to have to add a point, because if I'm on this asymptote in the middle, how do I know if my graph is going to go up towards the asymptote or down? I need some more information. So this is where we just plug in some values. If I wanted to find a point in this section, I'm going to plug in -8. What happens when I plug in -8? Can you see in your numerator you're going to get -6. In the denominator, I'm going to get a -1 here and a -9 there. I like to use the factored form when plugging it in. It makes your math a little bit easier to deal with. Right? What's easier, -1 times -9 or 64 minus 48 minus 7? I think this is easier math. What does this simplify to? -6 over 9, which is -2/3. So I can now plug that point on my graph. I have the point -8, -2/3. And now I have one point in that section. That is going to be enough. I need a point in this section. So bigger than y equals 1, I'll plug in 2. What happens when I plug in 2? Well, in my numerator I'll have 4. 2 plus 7 is 9. 2 minus 1 is 1. I get 4/9. Positive 4/9. So I can plug that point in. 2, 4/9. Now, when drawing my asymptotic behavior, I have enough in this section to draw this. I have enough in this section to draw this. I almost have enough in this section. Here I know because of that point and because there's no other x-intercepts, it has to go down. But in the other part, I don't know if it bounced off that x-intercept and went back down or went through and goes up. In order to figure that out, I might plug in another value like -3. What happens when I plug in -3? If I plug in -3 in my numerator, I'll get -1. In my denominator, I'll get 4 there and -4 there. Can you see that that's going to be 1/16? So I'm going to get the point 3, 1/16. Okay? After the fire, all the survivors can come back. So right before the fire drill, we plotted the point 3, 1/16. Since that point is above the x-axis, we can now finish our graph. We know because of this that our graph has to go up towards the asymptote because there are no more x-intercepts. So it has to continue and go up towards our asymptote like that. So there's our final graph. We had to add quite a few more points in part 3 in order to get the graph. Our x-intercepts and y-intercepts weren't enough. Our vertical asymptotes separated this one into 3 sections. And we had to get at least 1 point in each section, and in the middle section we had to find even more. Okay, questions for practice. R6 and 7.